Okay, so we're going to discuss in this video radian measure, right? Another way to measure angles besides degrees. Now you may be thinking, I know what degrees are. I've worked with degrees extensively. Why do I need to use this other measure? Right? And one of the reasons is degree itself is a unit, right? Now what we call these radians, these are essentially unitless. So if we want to describe things like angular velocity or anything like that, if we had degrees, our final answer would be like degrees meters per second, right? And we would have to, that's not intuitive, right? If I tell you something is 50 miles per hour, right? Or 5 meters per second, right? You have an idea in your head of how fast that might be, right? But when we added degrees, well, that really, that's just another obstacle there. It's not really that intuitive. So it would be nice if we just had a measure that was unitless. So if we work in this radian measure, then I don't have to worry about this degree unit at the end. It's just radians, and then it'll be just meters per second if we're describing some kind of velocity, right? So let's kind of describe here, figure out, introduce this idea of radian measure. So what we have here is a circle, right? Now a couple of properties of the circle, the circumference, right, the distance around it is 2 pi r, right, where r is the radius. Sometimes just pi times diameter, which diameter again is 2 radii, right? So r is the radius, right? So this would be r. And again, let me just label this the circumference. That's the total distance. If we start here and we measure coming all the way back around to where we started, it would be 2 pi r, right? A geometric formula that we've probably seen before. All right. Now, what if I didn't go all the way, right? I didn't go the whole circumference, but instead maybe just part of it here. Again, this is also r. So we're going to describe another quantity, what's called the arc length, right? And that would be this. S, right? So r is the radius, and then s is what's called the arc length. All right. And if you notice, describing the arc length in this way, we have a angle, we'll call it theta, that is kind of extended out by this arc length. Right? So the way that we define radian measure so to describe that angle theta in terms of radians, right, it is the ratio of the arc length, s, and the radius, r. Right? Now, we can see why it is unitless, right? Radius and arc lengths are both measurements of length, right? These can be, if this is in inches, that would also be in inches, right? So when we have inches over inches, the units cancel out, right? So we can see why both of these are units of length. So that's where it is unitless. Okay. So let's kind of take a look. Well, what is here? What is 1 radian, right? So if we look at this idea, what does 1 radian look like? And I know there's 360 degrees in one rotation. How many radians is that? Right? Some of you may know already, but let's look at why that's the case, right? So here I have some concentric circles, right? Concentric meaning that they share the same center. Right? And let's call the first one here, we'll define this having radius lowercase r. Right, so from here to here, r, r. Right? So if we have this here, another thing is that the arc length, if you think here, this is the length, this piece of string here, twine, is the length of the radius, which is also, I constructed in such a way that it's also the arc length here. Right? So in this case, S is equal to R. Right? So when theta is described by the arc length R, right? Well, going back to our ratio, theta R, or R over R, and that gives me 1 radian. Right? And what we want to show here is that this is independent of the size of the circle. Right? Now, in a lot of our discussion, we talk a lot about the unit circle, right? A circle of radius 1, and that's just a nice convention to let the radius equal 1, but really that is the size of theta is independent of the radius of the circle, because as we see here, for the larger circle, right, this is about the length of the radius. In this case, let's call this the larger one, capital R. Right, and we see here, right, that is roughly the same arc length there. Okay, and that should make sense here, right? Because now notice that it's the same angle, right? That angle doesn't change. So in this case, theta is S over capital R, but that is R over R, 1 radian. All right. So regardless of the excuse me, regardless of the size of the circle, okay, it still extends. It's still describing that same angle, right? We're just dealing with ratios of the radius and the arc length. All right, so that leads us to, well, how many radians in one complete revolution? Let's get a new piece of paper here. So now we can answer the question, how many radians in one revolution? Okay, so let's say we had a circle. Right, and we want to describe, right, one full rotation. Right. So in this case, theta, if it's of radius r, again, just a generic r, doesn't need to be the unit circle. Right. Remember, radian is described by the arc length, but in this case, the arc length is the circumference. R, right? But what is the circumference? Well, the circumference is 2 pi over r, right? The r is down here, and we get 2 pi radians, right? So that's why 2 pi radians is the amount of radians in one complete revolution. Okay, so now that gives us our conversion factor, right? 2 pi radians is equal to 360 degrees. Right, and again, that means that dividing by 360, or vice versa, divide by 2 pi radians, the conversion factor is this. That's equivalent to that, right? Depending on what units you're going to and from, right? You can reduce this also and use the simplified form, pi radians per 180 degrees, or 180 degrees per pi radians. Okay, thank you.